Okay, today we're going to look at solving a mixed circuit where we have some things in parallel and some things in series. And so how do we figure out then what the voltages and currents are at various points in the circuit? So there's two things that we need to know in order to do that. And A is Kirchhoff's laws. And Kirchhoff tells us that in any closed loop here on these circuits, that the voltages must add up to zero. So basically, if you start with 60 here, in this case, you've got to be down to zero at the end, which means everything in there's got to use that full 60, or everything in that loop has to use the full 60. So any loop that goes back to the battery will add up to zero. The other thing about Kirchhoff tells us that charge is conserved. So if there's a certain amount of charge flowing out of the battery, well, that's what has to flow back in. And so if that branches off, it'll come back together to make that same amount, so that we're not adding charge or somehow magically adding new electrons or something like that. So those are Kirchhoff's two laws, and they basically tell us then how these things add up and how they go together so that we can figure these things out. And the other real important piece here is Ohm's law, which is V equals IR. So you can see V's and I's and R's all over this circuit. And so if we know two of those three things, we can find the third. So you'll have to be rearranging that for I and V in this example, because all of the R's are given. The voltage of the battery is given. That's not always the case, and so sometimes you will need to solve for R, but in this example, and this is one where it's somewhat realistic in that resistances are often things you can read right off of something in a circuit. It's usually labeled, and voltage is often labeled right on a battery, as you know from using batteries in your life. So when I look at these circuits, I treat them like a game. I try to think of them like a crossword puzzle or Sudoku or something like that, where there's some things here that are going to be easier to find than others. There's some things that you just can't find at certain points, but then as you unlock some of the values for currents and voltages in this case, you were then able to find some things that you couldn't find earlier. So I always like to start with what is easiest. I always look at my circuit and think, is there anything that's like jumping out at me that's easy to do? And on this one, I think, well, I don't see anything here I can solve for. I don't see anything there I can solve for. I'm looking around. The only thing I can do in this case is actually solve for the total resistance, because I know all of the resistors in this circuit. That's not always the case. Finding R total is sometimes a pain. In fact, I'd like to do it easier. If I could find IO, I would just use Ohm's law to find that, because adding up the resistors is one of the more difficult mathematical parts of this. But in this case, we have to do it, so it's pretty good practice anyway. So I'm looking at these two resistors in parallel, and this one is in series with them. So if I can combine those two together and get an equivalent resistance, meaning I add them up as if they're in parallel, which they are, and then I can pretend that's one resistor, whatever number I get for that total, that's in series with this, I can add the two together and get a total resistance. So we got to remember how these things add up in parallel. So this is the first thing we're doing. Resistance adds up like so. So we get 1 over 25 ohms plus 1 over 15 ohms. These numbers were somewhat chosen at random, and they're not great for this example, so I'm going to do some rounding, which I probably shouldn't. But anyway, for seeing how just these things work, this is fine. And oftentimes the numbers don't work out so nicely as the whole number 2 or something like that. So we have these two things. I got to think of a common denominator, and for a common denominator for 25 and 15 is 75. And so if I take 3 times 25, I get 75. And if I take 5 times 15, I get 75. And so that gives me 1 over the equivalent resistance. And again, I'm only talking about these two. I'm making it as if there was just one resistor in this circuit, and then it was this and that one resistor in series. That gives me 8 over 75. I cross multiply, and I get my equivalent resistance for just these two as 75 over 8, which is 9.38 ohms. So that's interesting, right? That we had a 25 ohm resistor and a 15 ohm resistor in parallel, but when we put them together, it only adds up to a 9.38 ohm resistor, which might seem strange that how can we have these big resistors and it adds up to something smaller? Well, it's because it's like having two doors in a classroom. Let's say, yes, things bunch up there, but there's two ways to go around. So equivalently, this is like having one in series where everyone has to go through one door, but it's a wide door, let's say. So we have that, but now we have to take that equivalent resistor of 9.38 to get our total resistance here. So we're still working on that. RT needs to account for that 8 ohm resistor, but because we have this as one resistor now, it's like it's in series, and so we take our 8 ohms that we know from R1, add our 9.38 ohms, and we get a total resistance, RT, and I don't use RS or RP here because it's both together, of 17.38. So we can put that in here, 0.38 ohms. So now we know the total resistance. That's something. That was actually probably the hardest thing we have to do in this whole one. But again, you never know. Sometimes these look easy and they're hard, and sometimes they look hard and they're easy, just like a crossword puzzle or a game or anything else. But now that we know that, I know from Ohm's law, I can find I/O. So let's do that. I/O will be VO over RT. And so that is 60 volts over 17.38 ohms, and I get 3.45 amps coming out of this battery. So 3.45 amps. So that's the total current. That's all the current we have from the battery. So that's got to be, that's all that's going to go back in. And that tells me too, though, gives me something easy to do with no math, in that if it's 3.5 or 3.45, 3.45, 3.45, oh, it gets to here. It is not branched off anywhere. So this is like a hose with water in it. The water hasn't branched off, so it's all got to go through that resistor. So I know then that I1 is equal to I/O, which we know is equal to 3.45 amps. Great, no math involved. And that leads me to being able to figure out what the voltage is at that resistor as well. So again, we use Ohm's law. You see how important Ohm's law is for these. And that's going to be 3.45 amps times the 8 ohms. And that gives us 27.6 volts. So 27.6 volts are used by this resistor, meaning it's the charge in the current. The electrons carry that 60 volts, and there's a voltage drop here, so it's like a ball rolling down a hill to a lower level, and it's lost now 27.6 volts. So that's what we say, a voltage drop. At 60, it drops by 27.6. So what's left is what's going to be able to go through these guys. And again, that goes with Kirchhoff's law that it has to add up to 0 here. So if you have 60, you lost 27.6. You got to lose the rest of it in this one to get back to 0, and you got to lose the rest of it in this loop as well to get back to 0. So those two things will be the same. And so we can do that then by saying that 60 volts, that's the total, minus what this resistor has used, 27.6 volts, and that gives us 32.4 volts for each of these things, because again, one loop up to 0, the other loop has to add up to 0, and which they do when this one uses 32.4 and this one uses 32.4 volts. So remember that in parallel, the voltage in each branch is the same. If there was more resistors, they would have to split up that 32.4, but that's all that's able to get back to the battery here after that's used 24.6. And now we look at this, we're almost done here. We have two currents to find, so I could find I2 or I3 at this point. I have everything I need to do both, but since 2 comes before 3, why not do that next? And again, the order of some of these things is not necessary. Like I said, I could find I3 next, but I'm going to do I2 just because. Over R2, and so that's going to be our 32.4 volts all over 25 ohms. and that gives me a 1.3 amp current. So 1.3 amps goes there. Now, at this point, we have two options. We can say, to find I3, I can say that I know out of the battery 3.45 amps is coming out. 3.45 amps is going through there because it hasn't branched up. But then I know that of that 3.45, 1.3 amps goes down this branch, which means like a river here, the rest of the water has to go down the other one. They'll recombine to be 3.45 going back to the battery. But here I could say that 3.45 minus 1.3 gives me 2.15 amps. That's what's left there to go. So I don't even have to use Ohm's law there. If I wanted to, I could, just to double check, and it's often good to double check on these things. And so why not? I3 will be V3 divided by R3, and that's going to be 32.4 volts divided by, in this case, 15 ohms. And I get, within rounding, a slightly different number, but 2.16 amps. And so that's pretty close based on the numbers that we're using. So there's two ways to do that in the end. If you remember Kirchhoff's laws, then you don't even have to do the more difficult math, although Ohm's law is not that hard. But just ways to double check your work there to make sure that you're doing it correctly. So practice lots of these. They can be trickier than this or easier than this. There can be more resistors in series and in parallel, everything else. But this is a nice one to show you just some of the basic concepts.